Hello and welcome to this lesson on relations and mapping. I hope you are familiar with these areas. We have Greater Accra, we have Ashanti, Volta, and Northern. And we also have places such as Kumasi, Ho, Tamale, and Accra. But what is the relation between the places on the left and the places on the right? We know that the places on the first column refer to regions in Ghana, and the places on the right column refer to cities in Ghana. And if we watch carefully, all the cities here relate to one region or the other. Greater Accra, for instance, has its city as Accra. Ashanti has its city as Kumasi. Volta has its city as Ho. And then the northern region has its city as Tamale. So these are capital cities of these regions on the left. This is the concept behind this lesson we are going to look at today. We are going to start with what we call relations. We can relate two pairs of numbers in mathematics as well. For example, we can have 1 being related to 2 such that 1 is half of 2. So we can use this approach to solve for other numbers. We can say 2 is half of 4. And we can also say 3 is half of 6. Let's look at a few more examples. Let's assume we had these numbers on the left, that is 4, 9, and 16. And we also had a different set of numbers which are 2, 3, and 4. What is the relation between these numbers on the left and the numbers on the right? You can see that 4 is the square of 2. That means when we take 2 and we square it, we will get 4. Or if we take the square root of 4, we are going to get 2. So 9 is also the square of 3, and 16 is the square of 4. Let's do another one. Negative 1 is the negative of positive 1. Negative 2 is the negative of 2. And negative 3 is the negative of the positive 3. So we can see that in each case, we always have two pairs of numbers. Normally, the way we show relations in mathematics is to use arrows and ovals. Let's look at how we do this. We normally have the first items on the first column or on the left hand side in one oval, and we list various elements in that oval. We also have a second oval with elements that relate to those on the left. We then use a forward pointing arrow to relate between elements in the first oval and in the second oval. These are set elements. The first set of elements is what we call the domain, and the second set of elements is what we call the codomain. The codomain refers to elements that are formed by transforming the first set of elements in the domain itself. So for example, what we saw earlier in our introduction to this lesson involved cities and regions in Ghana. So we can redesign this by putting the cities in one oval, that is Kumasi, Ho, Tamale, and Accra, and we will have the regions on the right hand side in another oval, which is the codomain. So we will have Greater Accra, Ashanti, Volta, and Northern. Kumasi relates to Ashanti, Ho relates to Volta, Tamale relates to the northern region, Accra relates to the Greater Accra region. So whatever is on the left is the city of whatever is on the right. So the set of cities refer to our domain, and the codomain refers to the regions based on how we have designed them. Let's look at some mathematical examples. We have two ovals here. One contains the elements 4, 20, 26, and 100. And we are saying everything on the left is twice of everything on the right. And we have 4 elements that are listed as 10, 13, 50, and 2. 4 relates to 2 because 4 is twice of 2 based on the rule we have stated up there. 20 relates to 10 because 20 is twice of 10. 26 is twice of 13, and 100 is 2 times 50. Let's look at what we call ranges. Ranges refer to all possible elements of the codomain that have corresponding elements in the domain. What do we mean by this? Let's assume we have a few elements in a domain as A, B, and C. There are 3 elements in this domain, but in the codomain, which is set Y, we have elements Q, R, S, T. We have 4 elements. When we relate each of the elements in the domain to the codomain element, we have B is to R, A is to Q, C is to S. But you can see that T does not relate to any element in the domain. So we can say that the range refers to elements that have corresponding elements in the domain. So we will list our codomain elements in a set form as Q, R, S, but not T. We also have something we call ordered pairs. An ordered pair refers to all possible combinations between elements of the domain and the codomain written in a coordinate form. Let's assume we have this domain that contains 3 elements A, B, and C. And we also have a codomain which has Q, R, S, T as its element. Now, when we do our mapping, we have A is to Q, B is to R, and C is to S. T is not paired to anything. So when we want to write our ordered pairs, we are going to write it in a coordinate form. That is A, Q. That means A and Q are corresponding or relate to each other. And we will have B, R. We will have C, S. Note that T is not paired to anything, so we do not write it in a coordinate form with any other domain element. All we have to do now is to write the ordered pairs in a set form as A, Q, B, R, C, S, all in a set form. Let's look at this example. We have been asked to study this diagram and then find out what the domain is and what the codomain also is. We also need to state the range and write out all sets of possible ordered pairs. We also need to find the relation between the 2 sets. First of all, you know that the domain is normally written on the left side, and that transforms to create the codomain. So in this example, the set M refers to our domain. The codomain is what has been created based on the transformation. So in this case, it is N. Now, the range refers to all possible elements in the codomain that were created by transforming elements in the domain itself. However, 81 in the codomain, that is set N, does not have anything that is creating it from the domain M. So we do not include it as part of our range. Our range is a set containing elements 4, 9, and 25. Let's look at the ordered pairs. The ordered pairs looks at each domain element with its corresponding codomain element written in coordinate form. So we will have 2, 4, 3, 9, and 5, 25. But we don't have anything relating to 81, so we do not add it to our ordered pairs. Now we have also been asked to find what the relation between the 2 sets are. The elements in set N, as you can see, are squares of the elements in set M. That is, we will say 2 is the square root of the element in N. So if I take the square root of 4, I will get 2. If I take the square root of 9, I will get 3. If I take the square root of 5, I will get 25. Let's look at another example. Once again, we need to find the domain, codomain, the range, the ordered pairs, and the relation between the sets. The domain, as you can see, is set Q, and the codomain refers to the set that has the arrows pointing to it. So in this case, it is set R. Now, the range refers to all elements in the set R, which is the codomain, that have arrows pointing to it. So in this case, we have 3, 6, and 12. Our ordered pairs refers to each element that has an arrow corresponding to it from the domain and the codomain. So we have corresponding elements 1 in Q and 3 in R. We also have another one which is 2 in Q and 6 in R. And we also have 4 in Q and 12 in R. If you watch carefully, the relation between this set is that Q is a third of R, such that 1 is a third of 3, and 2 is a third of the element 6, and 4 is a third of 12. Let's now look at the types of relations we have in mathematics. We are going to look at what we call one-to-one relations, one-to-many relations, and many-to-many relations. Let's start with one-to-one relations. A one-to-one relation refers to a relation where only one image in the codomain is created by each input from the domain set. For example, if I have my set X, which is the domain, and I have my codomain, which is set Y, with various elements in them, you can see that at every point in time, one element in the codomain is created by an element from the domain itself. We do not have one arrow from the domain creating two different elements in the codomain. That means there is a one-to-one relation. Let's look at a few examples. Let's say we have this set M, which has 2, 3, and 5 as elements in it. And we also have this set which contains 4, 6, and 10. We can see that the set M is half of the set N. That is, 2 is half of 4, 3 is half of 6, and 5 is half of 10. So we can say that at each point in time, set M will relate to only one element in set N. Let's look at another example. Let's say we have this set X and we have this set Y. If you watch carefully, whatever is in set X is a fifth of whatever is in set Y. 1 in set X will relate to only one element in set Y, that is 5, because 1 is a fifth of 5. 3 is a fifth of 15, and 7 is a fifth of 35. Let's also look at one-to-many relations. One-to-many relations exist when multiple images in the codomain are created by individual inputs from the domain. For example, I may have this domain set X and I may have this codomain set Y. At any point in time, I may have one element in the domain set pointing to multiple elements in the codomain. For example, A may map to Q, at another time it may map to R, at another time it may map to S in the codomain. Let's look at an example. Let's say we have M. M contains 2, 9, and 7. And we also have set N, which contains 4, 18, 21, and 49. If you watch carefully, the elements in set M are factors of the element in set N, and there are going to be multiple images. For example, if we have the element 2, which in set M, 2 is a factor of 4, and 2 is also a factor of 18. If we take 9, we can see that 9 is a factor of 18. That is a one-to-one relation. But we have found a one-to-many relation on the 2. Another one-to-many relation sees us mapping 7 to 21 because 7 is a factor of 21 and 7 is also a factor of 49 because 7 times 7 will give us 49. So we can see that at any point in time we may have one-to-many relations. Let's now look at many-to-many relations. A many-to-many relation exists when multiple images are created by multiple inputs from the domain. For example, using our set X again, which contains the element A, B, C, and our set Y, which is our codomain, we may have, let's say, the element A mapping to Q and R. We may also have the element C pointing to Q in this case. As you can see, the letter Q in the domain has many elements pointing to it. That is, A is creating Q and C is also creating Q. Also, the element R is being created by A and also B. That means many inputs relate to many elements in the codomain. Let's look at an example of many-to-many relations. We have the set M and we also have the set N, being our domain and codomains respectively. We want to use the relation which says elements in set M are less than elements in set N. Now, as you can see, 12 is less than 18 and less than 20. 3 is less than 4, 18 and 20. 15 is less than 18 and 20 as well. Now, if we take the element 18 in the set N, you can see that it has 3 inputs, that is 12, 3 and 15. That means many inputs relate to many elements in the set N. Also, if you take 20, 20 has inputs from 12, 3 and 15 as well. So we take many inputs and we create many outputs out of it. We are now going to look at the second section of our lesson, which refers to mapping. Mapping refers to a type of relation where only one input maps onto an image of the codomain. We normally use this using some form of algebraic expressions as well. Let's say we have this set M and we have this set N. You can see that if we multiply the element in set M by 2, we will get the element in set N, and we will get only one of that. So we have 2 times 2 giving us 4. We can multiply 9 by 2 to give us 18. We can multiply 7 by 2 to give us 14. Let's say if we have a variable x which represents an element in set M, we will have to multiply it by 2 to give us y. So we can write an expression as if we multiply x by 2, we will get y. So 2x is equal to y. Or we can write this as y is equal to 2x. This is the concept behind the mapping we are going to study as part of the second section of this lesson. Let's assume we have been given this mapping for which we need to find a rule for. To find the relations between the pairs may become difficult. Let's say for the first pair, we have to look with our eyes and try and guess what may be happening. The first pair says 1 maps to 2. 1 maps onto 2 means we may have to multiply 1 by 2 to get the image 2, or we may have to add 1 to the 1, which is the input, to get our value 2. But we can't decide yet because any of those 2 options can give us our answer. So let's look at the other pairs to help us work this out. We have from the second pair 2 maps onto 3. If we are going to use the same rule, then it should help us arrive at our answer. So once again, the first one says the input times 2 should give us the image. So 2 times 2 should give us 3. And this is not possible because 2 times 2 will give us 4. That means our second option, which says the input plus 1 should give us the image, will give us our answer because 2 plus 1 is equal to 3. So the first option is wrong and the second option is the correct one in this case. So all we have to do is to check with the other pairs as well to ensure that our answer is actually true. So from the third pair, we will have 3 maps onto 4. Indeed, when we use our mapping rule, which is plus 1, we will have 3 plus 1 giving us 4. And for the fourth pair, if we add 1 to 4, we will also get 5. So indeed, the plus 1 is going to help us find our answer. Now, that will help us write out a rule. We will then have x, which is any element in the domain set, mapping onto x plus 1, which refers to the codomain element. We can rewrite this as x maps onto x plus 1. I hope this is fun. Let's do another one. Once again, we are faced with another problem. We are having a mapping being done without the rule being stated. So let's try and find this by guessing with our minds. We are going to use the pairs of the mapping to try and guess what the answer will be, or what the mapping rule will be. From the first pair, we have 1 maps onto 2. We have 2 possible options, the input times 2 or the input plus 1. This will not tell us anything now, so we go to the second pair, which says 2 maps onto 4. If we multiply the input by 2, we will indeed get 4. But when we add 1 to the input, we will not get 4. That means the plus 1 will not help us arrive at our actual answer, but when we multiply the input by 2, we will get our answers. So let's do this for the other pairs. We have 3:6. When we multiply the input 3 by 2, we will get our answer 6. When we do for the fourth pair, we multiply 4 by 2 to give us 8. So we can write a rule for this mapping. So for any element x in the domain, it maps onto 2 times x to give us our codomain element. We can rewrite this as x maps onto 2x. Let's try and solve this problem as well. We are going to use the first pair just like we did for the other ones. The first pair says 1 maps onto 1. But when we multiply 1 by 1, we can get our answer. And when we take the square root of 1, we will also get our answer. That is 1 raised to the power 2. When we take 1 plus 0, we will also get our answer. So we will have 3 possible options to choose from. Now, from the second pair, we have 2 maps onto 4. We are going to use the same options we have created from the first pair. That is the input times 1 and the input being squared, or the input being added to 0. Now, when we take 2 times 1, it will give us our wrong answer. When we do 2 raised to the power 2, we will get our answer 4. But when we do 2 plus 0, we will not arrive at our answer. So x raised to the power 2 refers to our answer in this case. And so the other options are not going to help us arrive at our answer. So indeed, x raised to the power 2 is our answer we are looking for. Now we are going to confirm this with the third pair and the fourth pair. If we have 3 maps onto 9, and we use our rule, which is x squared, we are going to do 3 raised to the power 2, which indeed gives us 9. And for the fourth pair, 4 maps onto 16 will be such that 4 raised to the power 2 will give us 16. So we can write the rule for our mapping as x maps onto x squared, or we can write it in this form as x maps onto x squared. Now we can also use a method to help us solve this without guessing. We can consider the rule of the mapping as if it was a line. So we can use the line equation to help us arrive at our answer. But there is an accompanying method we use called the difference method that we are just going to look at. So we assume the mapping rule is a linear equation, and we are going to use what we call the difference method. The formula is such that we will have the value a, which is in the linear equation formula, being equal to the difference between the codomain values divided by the difference in the domain values. First of all, let's find the difference between the codomain values. These are the values at the top. So we are going to take successive elements in the domain and strike out the difference between them. For example, the difference between 1 and 2 is 1. The difference between 2 and 3 is 1. And the difference between 3 and 4 is 1. At any point in time, the difference must always be the same between successive elements. Now we have to find for the codomain. The difference between 3 and 5 at the bottom is 2. And the difference between 5 and 7 is 2. And the difference between 7 and 9 is 2. So as you can see, they are always regular intervals. So we can slot this in our formula. The difference in the codomain values is 2, and the difference in the domain values is 1. So we are going to have a is equal to 2 over 1, which will give us a is equal to 2. So looking at our linear equation formula, we have found the value of a, and so we will put a is equal to 2 into the equation, and this will give us y is equal to 2x plus b, because we have found the a value. Now we are going to take one of the pairs of the elements we have been given to find our b value. For example, for the first pair, we will say when x is 1, y is 3, as you can see from the mapping. So y is 3 and x is 1. We have found a to be 2. So we put this into our equation and we can work out the value of b, which gives us 1. So now that we have found b, we can also slot it into our equation. And this will give us y is equal to 2x plus 1. b is now 1. So this y relates to the codomain values, as you can see on the mapping table up there. So we can say that the rule of the mapping is such that x relates to 2x plus 1, which we can write in this form as well. Let's look at another example. Once again, we are going to assume a linear equation model for this, and we are going to use the difference method to help us arrive at our answer. So let's go ahead and look for the difference in domain values. The difference between 1 and 2 is 1, 2 and 3 is 1, and 3 and 4 is 1. The difference between the codomain values is 2 in each case. So we put this into our equation and we arrive at a is equal to 2 over 1, which gives us 2. Now we put a is equal to 2 into our linear equation model, and we will have y is equal to 2x plus b. This is similar to the previous example we saw. But now we are going to take a pair of elements from the mapping that we have on the table. So we put x is equal to 1 into our equation, and we also put y is equal to 4 in order to find b. So we'll have 4 is equal to 2 into bracket 1 plus b. So we'll have 4 is equal to 2 plus b. So we work at b and we will have the value 2. So we are going to put b is equal to 2 into our continuing linear equation model, and we will have y is equal to 2x plus 2 because b is now 2. So our mapping rule will become x is such that 2x plus 2 is our codomain element. So we can also write this as x maps onto 2x plus 2. Let's try another example. Straight away, let's assume a linear equation model and use the difference method approach. Let's find the difference in values of the domain element. We have 1 in each case. And if we find the difference in codomain elements, we will have 3 in each case. So our a will become 3 over 1. So a is equal to 3. We put a is equal to 3 into our linear equation model, and we will have y is equal to 3x plus b. Now we are going to take the first pair of elements, that is 0 maps onto 2, to help us arrive at the b value. So when x is 0, y is 2, and we put this into our linear equation model to solve for b, and this will arrive at b is equal to 2. We are going to put this b is equal to 2 into the continuing linear equation model, and this will give us y is equal to 3x plus 2 because b is now 2. So our mapping rule becomes x maps onto 3x plus 2, which we can write in this form as well as our answer. We may sometimes be asked to find the inverse of the mapping. In other words, we may be asked to find the domain values by considering the codomain values as the input and working out the rule. It involves changing subject when you have the rule known. In this example, we need to find the inverse of the mapping for this. First of all, we may have found the rule of the mapping to be x maps onto x plus 1, which we can write in this form. That means we are going to find the inverse of the mapping y is equal to x plus 1. You can see that the y element refers to the subject in this rule because it is standing on its own on one side. So to find the inverse, we simply make x the subject. So we have to rewrite this as y minus 1 is equal to x, or x is equal to y minus 1. This is the inverse of our mapping. That means to find x values, we simply need to take the y value and subtract 1 from it. Let's look at the second example. This one has a mapping rule which states that x maps onto 2x plus 1. This means y is equal to 2x plus 1. So to find the inverse, we are rather going to make x the subject instead of the y. So to do this, we are going to have y minus 1 is equal to 2x. Let's now swap what is on the left hand side with what is on the right hand side so that the 2x will sit on the left hand side. So to find the value of x, we have to divide both sides by 2. 2 will cancel 2 on the left hand side, and we are left with x is equal to y minus 1 divided by 2 as our final answer. So this refers to the inverse of the mapping for the rule that we have been given. This brings us to the end of this lesson on relations and mapping. I hope you enjoyed it. Goodbye.